I think the text-to-speech is working at least. I hear you. But I can hear you. All right. So today we are looking at some samples from San Francisco Bay. And correct. I'm alone and there's no mask. And so this sample that we're looking at here is yeah. Like 8 minutes. So this is the same sample we looked at last time from San Francisco Bay, but this is the unprocessed version. Hi, Dangling. It's nice to see you. Let's see. So this sample hasn't been processed, which means a lot of the diatoms will be in their life position. I need to make one adjustment. Okay. Gotta get used to people talking while I'm talking. So here's some tintinids and diatoms, Athalasiosira, some of the things we saw last time. But there should also be some stuff that we didn't see before because this stuff hasn't been processed. So it's just rinsed out the salts, and that's basically all I did. I'm going to zoom out so we can kind of get an overview. And then I'm going to raise the stage up to 10. Yes, so Alan, my students are still on vacation. Good morning, Pacific Plankton. So, one of the things you will be able to tell that's different as a result of not processing it is things like these chaetosaurs are still in long chains together. So, in previous streams when we saw them, we just see a couple of them, but here you can see a whole sets of them in colonies. And these long spine-like projections that come out are setae. And as we talked about before, they can use to link the colonies together, but also chloroplasts can be put into them, so they can act to add surface area to the diatom colony. All right, I'm going to change the brightness a little bit. They do. So Dunstable Ramsey asked, do diatoms get bacterial and viral infections? There are diatoms that you can find that will be infected with viruses. I don't know that I've ever seen them because I usually process my materials with nitric acid, which gets rid of all of the organic material. Sort of just browsing around a little, trying to see if there's anything living in the sample, or that would have been living in the sample, that we could spot that we normally wouldn't be able to see after processing it, I mean. So here's another one of these chaetosaurus chains. And down here is a Thalassionemma chain. So you can see in life position, they had sort of formed a colony. Hey, Micah, how you doing? Of the Thalassionemma Pacific, you want a picture of that? Sure, I can do that. Hey, Cinnamon, how you doing? I think I took a picture of one last week, but it was by itself, not in a colony. And I also didn't share it with you, I guess. Hello? Sloppy D? How they're classified. Sloppy D wants to know how diatoms are classified. Yeah, I can do that. So there's actually a bunch of different sort of schemas for how diatoms are classified. The sort of classic approach is to look at whether or not they have a raphe, which is a structure that's on the diatom, and also whether they are bilaterally symmetrical or radial symmetrically. So we usually refer to the sort of radially symmetric stuff as centric, and stuff with a raphe as raphid. And there's some that don't have a raphe but are bilaterally symmetric, which we would refer to as araphid pennate. Yeah, raphid. And so that's the sort of highest level classification. Oh. Yeah, welcome in, Steve. I know I've seen you on Pacific Plankton stream before. All right, I'm gonna just set the speed to 7 and collect this image. One for Pacific. And then I can talk a little bit more about diatom taxonomy. Oh, that's cool. Sloppy D. So at the top level, the phylum level diatoms are in their own phylum called Bacterial phyta. And then there's a whole bunch of classes, but the centric diatoms are largely in the Costonodisca fascia. The araphid pennates are typically in Fragillaria fascia, and then the keelraphid diatoms and the raphe diatoms are in Basilaria physia. All right. Hello, Mallory. So the diatoms that we have on here, Thalassionema, I think, are an example of an araphid pennate. So in that scheme, they would fall under Fragillaria physia. So I don't know how much more detail you really want me to get into on the taxonomy. It's kind of boring, but a lot of the diatoms are divided up by their sort of ultrastructure of their skeleton. Okay. Sure, Sloppy D, no problem. On the diatom that we're looking at, the Lesionema, if we zoom in, which I can do now, the diatoms are being held together by a little bit of EPS that comes out right here on the sides. And then it's got areolae right here. The little structures are sort of openings that go into the valve itself. And then these are the two valves that make a frustule right here. You can see sort of overlap each other a little. So this is one cell, another cell, another cell, and another cell. Not sure what that is. Then a flagellate, maybe? Just a piece of something. I think it's just broken off in a weird shape. Uh-oh. I'm getting raided by last miles. Text-to-speech is going to get crazy. I think I should take this off for a minute. Okay, so... Hey, Last Miles. Thank you for the raid. I've been trying to use text-to-speech today to keep up with my chat a little bit, but I think I'm going to... think the raid's going to create a problem with that. Uh-oh is the appropriate response. Yeah, huge raid. I want to welcome everybody in. Today we are looking at some plankton from San Francisco Bay, and the sample that I'm looking at right now is actually one that I didn't process other than just to rinse it to try to get some of the organic matter out of it, the clay organic matter out of it, and also to remove some of the stench because it was pretty stinky. But I wanted to try to see if I could find some things that were in the sample that weren't just diatoms. In the previous stream, we looked very closely at a number of diatoms from this sample. So diatoms are a type of algae that lives in aquatic systems, which you may be familiar with. And there's other things that can create siliceous skeletons, like this radiolaria, for example. But I kind of wanted to see if we could find any of the other things in the sample, and also get a little bit of a view of the diatoms in their life position. So sometimes it's nice to be able to do that. You know, it's nice to be able to see ultrastructure as well, which is what we mostly get when we look in the scanning electron microscope. But I think that for some of it, it's nice also to be able to occasionally see what do these things actually look like where they're living. You know, how do they look like with their valves all together, or how do they look like when they live in colonies? So I'm Diatoms Tac, and on Wednesdays and Saturdays, I usually stream from my scanning electron microscope. And Last Miles has been in here before when we've streamed. I think he brought in a big raid before, probably because he gets to the end of his stream, and then I happen to be starting my stream right about then. So I want to thank him again. I watched a little bit of Last Mile's stream, you know, when I came in and was trying to get things set up. So I didn't talk much. I really didn't talk at all, actually. I just sort of watched what was going on. But he's a very entertaining streamer. Mostly he does coding, I think, and but he talks about whatever a lot. Um, this is an example of something that we wouldn't be able to see if I had treated the samples the way I normally do, which is starting off by putting them in nitric acid to get rid of all the organic matter. And one of the things it does is it kind of often breaks down the organic parts that hold the diatoms in colonies together. So with this really nice ketocerous spiral here, when they're in their life position, they create these long sort of DNA looking like spiral colonies. And in the setae, which are these long hairy looking spines that are coming off of them, kind of help hold them together somewhat. But a lot of times when you get rid of the organic material, what happens is that all the little colonies break down. So we end up just seeing individual valves instead of whole colonies, and we lose this sort of spiral nature of the organism, which is, it's fine if you're looking really closely, you're trying to see ultrastructure, but I think if you wanted to get a sense of, how do these things actually live, you really need to occasionally try to look at things in their life position. So it's sort of exciting to see. And then also there's some other things in the sample that aren't diatoms, as I mentioned, that I occasionally want to see what else is in there that we could get on the SEM. I've seen some tintinids so far as well. And besides just the diatoms in their colonies, here's another example of this is, I believe, a Kurethron, which is a really cool looking diatom with these sort of radiating, or maybe it's, I think it's a Kurethron. It has these really long setae like the ketocerous, but they radiate out in every direction. So this is a really cool example. I would not probably have been able to see this if I'd have processed it. I'd just end up with a single valve of these. But you can see here they are living in their living position. They have these sort of radiating setae pointing out in every direction. And then they live in colonies that are all in these colonies that are all attached together, which we can see very clearly because we, in this case, I didn't process them. So you can see these rows or bands of these things all radiating out from the central colony. What a really cool looking diatom. And I'm excited to be able to find one of these to showcase for the stream. So these samples, I should point out, are ones that were sent to me by one of my moderators here in the channel, Pacific Plankton, and we are good friends, and she occasionally will send me samples from San Francisco Bay, and then I will slap them onto my SEM, and sometimes with processing, sometimes without processing, and super excited about this one. And I also put this is a sample from, was collected in mid-December by Pacific Plankton from Plankton Toe. And then she sent it to me. It arrived like the week before Christmas. And so I processed some, and then we left some unprocessed material like this. So here I can jump back and see what chat's been saying. I was trying to keep up with chat with my text-to-speech, but I've just given up on it with a giant crowd of people coming in. Oh, you think it's Bacteriastrum? Okay, totally possible. It doesn't have those sort of weird root-like structures that are poking out, but it does have sort of a Bacteriastrum shape to it, so that's totally possible as well. So let's see. Glypht says, I only know blue-green algae really, but I know there are many species. Yeah, there's a really large number of diatom species, hundreds of thousands, probably up to millions, in terms of what we don't know or what could be cryptospecies. And that estimate comes largely from the fact that when we look at the known world and we start to really explore some of the unknowns or the things that we thought were the same species in, say, Europe and North America, what we find is that once we start really looking closely at it, what we thought was one species is typically something like 5 or 6 species, and maybe more. And so, we could be off by a whole order of magnitude on some level with respect to what we think our species are really more like genera for diatoms once we start to get to the actual sort of finest resolution of that. So let's see. Mama Bonbon is here. Hello, Mama Bonbon. Tropical Geek as well. Welcome in. Well, when I was watching you last, Miles, you were eating some sort of stew and talking about a homemade stew that you made or something. But there was some coding going on, and you were mad about movies, Green Flash movie. I think is what you were talking about, which I don't even know what that is. Little Chook is here. Hello, Little Chook. Welcome in. It's nice to see you. Let's see. This new Pokemon update is wicked. That is a great way to think of diatoms. You have to collect them all, and they all look totally different from each other. And taxonomy is not totally different from Pokemon, to be honest. My daughter plays Pokemon, and it's basically just taxonomy for, digital creatures. So, let's see. How do we hire these guys to fight COVID? Well, we can't. Diatoms have been used to fight cancer, though. So we'll give them some credit for that. Let's see. Got a little rain there, little Chook. You're staying warm and dry. That's good. You don't want to get your, your feathers ruffled in the rain. So, yeah, bay diatoms. Let's see. Question from Les Miles. These things have been with us for 500 million years. They predate just about everything. Diatoms have been around basically since the Jurassic. So they haven't been here quite as long as 500 million years. Let's see. You think it's Bacteriastrum colony? Okay. And I thought maybe it was Kurethron, but Bacteriastrum is fine. So I don't actually study marine diatoms. I study freshwater diatoms, but good enough to get some idea of what I'm looking at usually. And Pacific Plankton has been looking at them very closely, especially since I think I started helping her with some of the diatom at Taxonomy. And I think she's surpassed me at this point. Some things she just knows better than me because she sees them more frequently, which is cool. So, all right. So let me find something else really quickly here to image. We've got a bunch of really things that we normally see when we look through some of these San Francisco Bay stuff. Thalassiosira, Costinodiscus, Chitoceras, Ditillum, a lot of the sort of regular stuff, and I'm trying to avoid those just because we've seen them so many times. Not that they ever get boring, but here's like, for example, a giant Thalassiosira. This one's really huge. And just one valve-face photoportula right here. Oftentimes when you see Thalassiosira, they use this sort of started process here in the center to exude out a little sort of thread of EPS, and then they use those to connect to other Thalassiosira of the same species in a colony. So they'll make a big long colony of these things. Not all the Thalassiosira continually live in colonies like that, and perhaps these don't actually live in colonies. But the organisms still have that structure, and more commonly Thalassiosira have those than other organisms. Here's some example of some Pseudonitzia, and Pseudonitzia also live in a colony. They kind of slide past each other a little bit along the sides and use that to wiggle around a bit. And these are one of the few diatoms that actually can become toxic. So Pseudonitzia um, so-called named because they are similar to a species, a genus called Nitzia. And maybe I'll get a nice colony picture of these two next to each other, so I can come back to chat and look at the questions a little bit more. So for the SCM, what I normally do is zoom in a little bit so we can see a lot of the structure. And if I'm going to try to get something nice as an overview shot, I first will zoom in and take the picture, and then I can just zoom out as much as I like the magnification until the thing that I want is basically framed the way that I want. And this one just happens to be right at a nice 45-degree angle, so I don't even have to fidget with the angle or the rotation or anything. And then change the beam intensity so that it's sort of geared for a resolution that I want, and the speed, set the speed to the speed of the beam to something that I want. And then oftentimes I also will fidget a little bit with the brightness and contrast settings. So I'm taking a picture basically, or something like a picture that's being built as we scan over the material, and this will allow me to have a nice pretty picture that I can then share with people. So if you're interested in seeing any of the pictures that we've collected on the stream, some of them will show up in the little slideshow at the bottom, but I also share them into both my Discord and often to Instagram, and sometimes if they're really nice, I'll also post them to Twitter or something like that. So if you're really interested in seeing some of them, I usually will colorize them, try to make them look pretty, and that sort of thing. Well, let's see. Miss Daisy D is here. I don't know. Oh yeah, we gave a shout out to Miss Daisy D. Good. Sorry, I missed it. She got her Christmas card that I sent her. That's nice. I spent a long time. I spent like a whole day making Christmas cards for people. And since Daisy sent me samples of Luna moss earlier in the year, and we took a look at them on the scanning electron microscope, I thought it would be nice if I sent her a Christmas card. So, what are the connecting structures made of? In most cases for diatoms, this connecting structures are wetware. They're just basically EPS that the diatom sort of exudes out, and then it's either shared between the cells or whatever. It's basically sort of a snot-like stuff that kind of holds it together, a slimy coating. There are also some mechanical components, some sort of hardware that hold diatoms together, and so you'll sometimes see a groove or a notch that fits together, or they've got spines that kind of knuckle together, like your knuckles. If you tried to put them together like this and then pull them apart, you'll find that it's very difficult to do because the bones are sort of knuckle shaped, obviously. But the diatoms can do the same thing. They can have spines that have little knuckled ends like that, and sometimes they'll have those sort of structures that will hold them together. So diatoms are not two atom molecules. No, the word atom means part, and diatom means two parts. So technically, the word diatom just means an organism that has two parts, and all diatoms have a frustule, which is their whole cell wall, which is what we're looking at here, the cell wall, and they're divided into two parts, or two valves that come completely apart. They disarticulate completely, and in life, when they're alive, they can expand them out and grow new valves basically inside of the existing valves in order to replicate. Yeah. So Miss Daisy D, you drive safely. Don't worry about it, and have fun lurking. There was never a Green Lantern movie. It didn't happen. Oh, okay. Green Lantern. Got it. Can we please make a Pokemon type game, but all of them are diatoms? I can try. I'm not very adept at drawing cartoon-like things. Maybe you could help me do that. Let's see. Drive safe, Miss Daisy. Yeah. Or have somebody drive you, Miss Daisy. I mean, isn't that a movie? Okay. Indiana Jones and the Temple of Doom, that was okay. I agree. Those were okay. Yeah, they got worse, I think, a lot of them. You'll get me Kurethron soon. Okay, good. Uh, are plankton microscopic shrimp? Oh, okay, good. Pacific Plankton answered that question. Do we have any party dudes? I don't know, not yet. Maybe. You're amazed at the speed of the microscope. I was using an SEM in the early 90s and everything took a minute for a scan and we'd print out a Polaroid. Yeah, I did the same thing. That's the kind of SEM that I learned last Miles. That's the kind of SEM that I learned how to use an SEM on, was the old kind with the Polaroid. And it took forever to get good pictures. And then you got like one photo out of a session that was really good. You usually felt like you did something, useful with your time. Um, it's a lot more challenging in the old days because you had to do all of this uh, sort of adjusting the beam manually, and it just took forever to do. And you never know when you did it if it was good because wasn't it wasn't clear. Um, What the Pax? I can't remember what this thing was called. Pseudonitzia paxillifera or something like that. Um, so I don't know. Yeah, the technology for the SCM is definitely improved quite a bit, and the thing that I really like that this SCM can do, that I get really excited about, is actually when I tell it to rotate. Even if I'm not in the center of the carousel, it can turn and recalculate where the center would be and move me back to where I was. And you don't know how much time that would save, because in the old days, if you wanted to turn a specimen, you had to turn it like over here with a crank on the inside of the actual SEM. And there's still SEMs that are made today that work this way, where you have to actually turn the stage manually. And then you'd have to just turn it a little bit, move the diatom back into the field of view, turn it a little bit, move it back into the field of view. Otherwise, you could just totally lose track of what you were looking at. But this one just has a button that says like keep in field of view, and then I turn it and tilt it. I can do anything to the stage, and it will basically just it'll calculate where the center of the stage is currently, and it will put me right back at that spot, even if it's tilted like 40 degrees or something like that, which frankly to me is just crazy, and was one of the reasons I was immediately sold when we were trying to pick out which one of the SCMs we wanted to purchase for my lab. And it was like, that feature is just going to be amazing, where you can just turn stuff and tilt it and it stays in the field of view. And it's one of the things that I don't know why other SCMs, why they didn't think to do that, because it's such a pain in the butt to try to figure out how to do it manually. And a computer can just calculate it for you. I mean, it knows where you are in its X, Y, and Z positions. So it just calculates where that is, and then reconfigures it to the right place. And it is so much easier. And, when I show that to my colleagues that are also diatomists, they're like, that's a huge bonus, because a lot of times you're trying to like see around the edge or tilt or turn it, and to try to get a better view or a different view of something. I mean, in here we're mostly just taking pictures of things flat because I'm just trying to showcase things. If we wanted to see tilted diatoms also, we can just do something like look at one of these, right? So here's one that's tilted, and I didn't have to turn it to get the diatom tilted the way I wanted. I just found one that was, positioned that way. But if, let's say I was looking at this Rimiportula structure and I really wanted to see like down inside that tube, I would have to tilt the stage in order to do that, and then I might lose the specimen that I was looking at if I did that, which is a giant pain in the butt, Anyway, so fortunately we don't have to do that with this SEM. We can just basically click a button, and it is amazing. So, like I said, I grew up on the same kind of hardware you did, we used an old-fashioned SEM, um, and for my PhD, they just had an old JEOL that was still running, and I have to say it was a giant pain in the butt, but at the time I didn't care because I was just so amazed at the images you could get out of it that I just was like, oh, not a big deal. I will sit here and turn this thing around very slowly for an hour if it takes that to be able to see the structures that we can see. So, but now I can just do it with a click of a button and a little bit of a mouse wheel, and boom, we're looking at something cool without much work. So, for the diatom stuff, it's super useful, and for describing species and that sort of thing. So I'm not complaining about it at all. So this is a pretty nice view. I was just trying to talk my way through an example, but I'm just going to go ahead and take a picture of our Thalassiocyra that we're looking at here. You can see the rim of Portula, which is a structure for Thalassiocyra, just has one of these typically sticking out somewhere, and it looks like a little chute or tube sticking out the top. And then all these things on the side are strutted processes, and this is a row of spines. It goes all the way around the outside edge. Spines differ from these sorts of things in the ultrastructure of diatoms in that spines are solid and they're ornamental. In other words, they only go from the surface out. They don't actually go into the valve at all. Whereas things like Erymoportula or strutted processes are not considered spines because they're actually little holes that go all the way through the diatom valve. And they're used for different things. The spines are basically just ornamental or potentially used for something like protecting the diatoms from being grazed or something like that. Whereas the other pieces are for real, things that are used by the diatoms. How they're used is always not totally clear to me. And thank you, Pacific Plankton, for handling all of my messages and shout outs and stuff right there. Hopefully someone sent out a squad command so that they could see other microscope streamers, my friends here on Twitch, especially Del Maximum and Pacific Plankton and A Tiny World, who are some of the really great microscope streamers that you can check out on Twitch. So I also will stream sometimes from my light microscope at home, but on Wednesdays and Saturdays I like to come into the lab and do my SEM stuff. Steve Mandel asked, what software do I use to colorize? Prior to today, I mostly just used Lightroom, Adobe Lightroom, to colorize. At Christmas, I bought myself Procreate, and I've been teaching myself Procreate since Christmas, basically. And so I'll usually start in Lightroom, export it on my iPad from Lightroom into Procreate, and then I'll just tweak it a little bit in Procreate and maybe add a little additional color or some of the sort of fine-tuned painting of the images. And so I really like being able to have a little bit extra control, but it takes a lot longer to use that combination of things. And I thought one of these days I might actually try to stream once I figure out how to connect my iPad to a computer. I might stream myself doing some of the colorizing. It's relatively easy, so it's not handshakes. Yeah. Okay. Yeah, so Manifesto, somebody answered that question. There's a scale at the bottom, and also there's a text scale, a label at the bottom down here that tells you the view field. So at any time, if you can't see the scale when it gets down to it, there's a view field, and our current view field is that we're looking at is just about 37 microns across. So, and it looks like somebody answered that question with a bunch of math for you up there, including last miles. So, let's see. I'm so far behind in the chat because there's so many people, it's hard to keep up with. When the Polaroid was great, except for the big skipper. What model SEM do I use? Oh yeah, Pacific Plankton took care of that question. It's a really pretty specimen, Thalassiocyra. Coming from an electronics background, this is Maddie. Not knowing much about SEMs, the technology is interesting. Learn to build up on physics knowledge. I'm glad I found the channel. You're wonderful explaining stuff. Thank you, Maddie. I put some of these sort of explaining diagrams in here for just this purpose, in case people had questions about the scanning electron microscope and how it works. You can find them just by going on to Google and Googling an answer if you'd like. So this is sort of the upper part of the scanning electron microscope is the gun, and basically there's just a little plasma cloud being created by a tungsten filament that gets electrons sort of collect in this chamber up here called the Weinhold cap, and then it's got a negative charge because they're electrons, and there's an anode down here that basically pulls them out of the chamber because it has a positive charge, pulls them through the scanning electron microscope, and they are sort of form a beam. Any beam of any type has some scattering associated with it, and so what happens is that an SEM uses magnets to refocus those beams, and just like lenses do in a light microscope, basically you need a couple of them to keep the beam where you want it, and the magnets help us basically position the beam when we're aiming it down on the sample. And then it passes through a little ring. In my case, I have that backscatter detector pulled out. It's not engaged, but we could put it in. And then it hits a sample, comes out of here, which is the cone, or sometimes referred to as the pole piece on a scanning electron microscope, hits the sample, and then the electrons basically will knock electrons out of this material, whatever it is. And this poor ant in this case is the thing that we're looking at. And then those electrons basically are pulled towards a secondary detector. And the secondary detector has a positive charge, just like the anode does up at the top. And what happens is the electrons that are coming off of the specimen, if they're pointed towards at any particular point, if they're pointed towards the sensor, they're brighter because more electrons will hit it. And if whatever it is pointed sort of away from the sensor, it will be darker. So just like a flashlight, if you were shining it into there, the secondary detector sort of functions like a flashlight, except for in reverse. It's collecting electrons, and then basically you have a photosensor inside the secondary detector that lights up. The more electrons hit it, the brighter that pixel is, and then basically it just scans across the specimen pixel by pixel and says bright, dark, bright, dark, bright, dark, but quantifying it. And that gives us a sort of a black and white image. So it's kind of a cool way of getting at that idea that we're using electrons in place of light to see things. So that's my sort of non-engineering angled explanation for you of how this sort of process works. But if it looks like where we're looking at some sort of fuzzy internet image from the 90s loading, so you see that it looks like it's sort of building it or downloading it. That's what it's doing. It's scanning along and pixel by pixel sending that information to the computer for each electron interval that it hits. And then the beam intensity on a scanning electron microscope for this scanning electron microscope is sort of equivalent to the spot size in old microscopes, but it is how big the beam is. So if a beam is kind of big, then there's a lot of fuzz around it, but it gives off a lot more electrons. So if you want something to be a little bit brighter, you'd usually turn the beam intensity up. If you turn the beam intensity down, it's necessarily a little dimmer, but what happens is the beam gets smaller, so your resolution gradually improves, so there's less bleed in the actual information that's coming into the sensor. And so you can use that to get a good handle on high resolution images versus sort of, if I was doing something zoomed out like this, I might want to switch to a beam intensity 10 because I don't really need to see any of the details at this distance. If I'm zoomed in on something, like say we picked this Ellerbeckia, oh no, what is this? I don't even know what that is. Oh, something interesting. If we were zoomed in on this thing, this diatom, it's the whole valve. I don't know what that is though. That's an interesting looking diatom. Maybe Paralia. I don't know. Normally I would see some sort of poker chips over here, but I don't know what this one is. But if we were zoomed in really close, like here, for example, and we don't really want to have a really wide beam. We want to narrow it down so we can get a higher resolution image. And you can see how it makes it dimmer, but the details are much higher. And we resolve the problem with this sort of resolution by changing the speed. So if we slow the speed down, instead of the beam moving quickly across an area, it moves more slowly, and then basically there's a lot more detail because it's getting more information for every second that the beam is sitting on the specimen. So we can use that to get a pretty good handle on a high resolution image just by making the beam smaller and then increasing the density of how many points of information it's giving back to us, right? And then, of course, there's still a problem with the brightness of the image. So, why don't we just turn it all the way down to the minimum size? Well, then we don't get as much electron information back from the sample. So we're always making some sort of trade-off decision-making about, how bright do I want it to be? How much detail do I need? And how critical is that with respect to how much information we're getting off of the sample? So for this, what I might do if I turn the beam intensity down is then change the brightness and contrast to try to adapt to it, the fact that it's a darker image, right? I could also just fix it in Photoshop later, but it's better if I have basically an image that's closer to what we actually want from the sample itself before I do that. So I'm not losing information from over-brightened pixels or from areas that are just basically too dark. And you can see over here, really pretty, I think that's a Costodiscus. The surface of that Costodiscus looks like Christmas over there. Okay, so speed 7, beam intensity 7, and I'm just going to take a picture, and then I'm going to try to get back to chat again. This is the problem, always trying to keep up with chat while I'm digging around with these. So, yeah, okay, so that was for Maddie. Sorry about the super long statement there. I stream from the SCM on Wednesdays and Saturdays from 1 to 3. And I say 1 to 3, and then I'm usually here from 1 until 4. And I usually come in at 11 and start tinkering around getting my samples together. So, but I'm actually in the stream for that part, right? So, background was materials physics. Cool. Oh, crystal boundaries. There's some really cool stuff you can put on the SCM with electronics for material sciences. Okay, Squilky is here. Happy New Year to Squilky. And at the end of our last raid, which was Wednesday, we raided Squilky, and it just happened to be her birthday. So, and now we're here. Happy New Year, everybody. If I forgot to mention. Sam Shang TV says, I'm so pleased Twitch algorithm led me here to the stream. Well, we're excited to have you in. Welcome here. Econ Greg, also somebody give a shout out to Econ. Oh, they did. Okay, good. There's a bunch of great streamers in the channel with me right now that come to visit us periodically, and I just want to make sure that everybody knows who to check out. So also hello to Headshot Specialist. It's nice to see you again. I like it when people have come to the channel and then they come back to the channel and hang out with us. Other streamers or non-streamers or anyone, I just kind of like to have people stick around. So what are we zoomed in on right now is diatoms, and there's a channel command for diatoms. Let's see, looks like candy from the 1960s. Well, I don't know, I guess it could be kind of like candy. Oh, there's like sugar candies or something, maybe. What is the limit? My super zoom limit. Normally the limit of what I can do for this scanning electron microscope is something like 150,000 times magnification. So a normal light microscope has a limit of about 1000x, and the scanning electron microscope that we have kind of things get kind of fuzzy after about 150,000 times. So about 150 times stronger than a light microscope. Um, Before it just kind of like, I can give you an example of what I mean. Let's see. I don't even know what kind of diatom this is. I'm just going to put down unknown. That happens sometimes when I'm looking at marine stuff. I'm sure the Pacific Plankton has some idea as to what that could be. And I'll give you some example. So let's see, we go over to this, we saw this sort of cool structure on this Cossinodiscus over here, right? In the field of view that we were looking at before. You see this sort of cool floral print kind of structure they have on the outside of their areolae. And we can get this a lot better than the focus that it's in currently, right? So, because it was focused on the other surface, now we're focused on the actual surface here, and I can keep zooming in. So we're not even close to the limit of our zoom for this particular SEM right now. It's a little dark, but our image is still pretty clear. So, I mean, I could take a picture. You can see all the detail of this silica that's on the structure of this. If I keep zooming in, right? So now we're really close to that same material. And I get to the point where it starts to get hard to focus. And I can fix this by decreasing my beam intensity again. So I can lower my beam intensity down to 5, right? So now I went from 7 to 5. You see how the image got a little darker, but I was able to get a little bit more resolution out of it at 5. And I could potentially go down as far as 3, right, without any problem. But see how much darker my image is. So I've got to make some sort of adjustments for that. I slow my beam down, and I can do an auto brightness and whatever. Right now we're at 100,000 times magnification, just for clarity. So, I can get this sort of bright enough. And then the problem is, of course, trying to make a trade-off between how bright we want it and how clear the focus is and how fast it's got to move in order for us to do that. So let's say I got this thing nice and tightly focused, even at this magnification. So we'll move this little box down to something really small, then we can get it in focus even though it's tiny. It doesn't have to scan the entire page, so that's sort of a trick. And we can get really tight focus on that. But then, so we reach some point where no matter how zoomed in you get, it's not like there's a physical limit, it's just like a focal limit, right? It's about my ability to resolve things clearly. So we could lower the beam intensity again down to 1 and zoom really close in on this thing. But at some point we're going to have to lower the speed quite a bit. And then I'm going to have to wait a long time to really get that image to show clearly, right? So that was our speed at 7. I moved it down to 8 to get this sort of picture. But you can see it's still kind of grainy. And that's because our beam intensity is set at 3, and it really doesn't look good at 3 unless I take it down to at least a speed of 8. If I take it down to a speed of 9, then we have to wait a half hour for a photo, right? So you can see what the problem is like basically making some adjustments. This SEM goes to a speed 10, and it takes an hour and a half to collect an image at 10. So that's why we don't do that on stream. And typically I don't do that at all. I think I've had one time where I took pictures at 9, and then I was like, I started it, I had something really gorgeous, and started it, and then I went to lunch. And I came back and the SEM was still collecting the image. So that's an example of me using my time effectively and still getting a pretty good quality image out. So we spent a lot of time on this sample, and I didn't mean to. It's just we got that big raid from last miles, and then I started talking about stuff and blah, 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 like normal. So why don't we try moving around? There's another sample that's like this one, that's over here. That's another cool thing about the TestScan Vega 3 that we're using, which is that I can just click a button and it moves us around to different samples. So I've got a nice seven sample carousel in there right now, which will allow us to very easily sort of pick which one of these samples we want to look at. And I can kind of bounce between them pretty easily, which, you know, I'm happy about, because I can see a whole bunch of things at once. Well, that one is a Paralia right there. So, for sure, this is the way they typically look. They have sort of poker chip shaped margins, and up at the top, this sort of crown shape. So that one is definitely a Paralia. That's a whole cell right there. And then it's got little spines connecting between it and the next valve. And then it's got this whole series of sort of stacks of internal structures here before it gets to the next valve. But you can see between valves, it's going to have the same sort of ending structure right here. So it's a pretty cool one. I don't know if, I guess I could get a picture of a Paralia. I don't know if we've ever done Paralia pictures on, for Pacific, but we can get one for you. I can stop talking for a little bit, maybe read a little bit in the chat. And I'm going to bring my beam intensity back down so that we get a nice clean image. And then I'm going to rotate the stage a bit. So I want it to be maybe 340. Well, I'm getting pretty good at guessing what the rotation I needed was. That was almost perfect on the first try. So I like to get them at a nice 45-degree angle just so I can maximize the image, right? I need to maximize what's on the screen because people don't want to see the garbage around it. They want to see the thing that's the subject of my photo. So speed 7 looks good. Beam intensity 7 looks good. And I can hit this and then hop back over into chat and see what's going on. Let's see. Okay. Let's see. Squilky birthday raid. Yeah, that was fun. I'm really happy I didn't know it was your birthday. So it was nice to be able to raid and then have it be special. So it's like a barrel from Donkey Kong. That's actually a really good observation, Pandemic Watch. I want to flex on you too much, Del. Let's see. How far back am I? I never see the little ones this close. I will work on finding out. Yeah. 500 nanometers visible light wavelength. Yeah. So we could get down below the visible light wavelength pretty easily. Oh, look at that. We have a gift subscription. I'm sorry, I totally missed all the actions. I'm going to get back to those. It's hard enough for me just to keep up with the chat. Rob Moore, would the electrons this thing is firing hurt if you put yourself under the scope? Well, first of all, you have to be in a vacuum to be in the microscope. But the second part of that question is, it would knock little electrons out of your hand. Would you feel it? Probably not. I mean, like if you had a tactile sense that you could have inside of a vacuum, you probably couldn't feel it. It probably wouldn't remove enough that you would notice. But you know, you can't put your hand inside the vacuum in the first place because that's going to hurt way more than the electrons would. Okay. Hey, Frecht Chemist. Somebody did send a shout out to Frecht Chemist, didn't they? Yeah, okay, good. Pacific Plankton's been busy today. She's been handling all of my shout outs and everything. She's such a great mod. You know, last year I was going for mod of the year with Pacific Plankton, and I feel like maybe this year she's trying to outdo me, you know, as mod of the year. So she's doing a great job right now, handling questions I should have answered, but I didn't have a chance to. Looks like a car filter, a little bit. Let's see. Sarah's here. Hello, Sarah. We still need to figure out the lizard thing, Sarah. Let's see. You've never worked with sputter-coated stuff. You're jealous. Well, you can come work in my lab if you want. I'll set you up. We got a sputter coater. You can burn holes in things here, you know, just as easily as you could there, probably. I don't know. We probably don't have the right sensors on it for you to burn holes and stuff. Thank you for the gift sub to Econ Greg. It's very generous. Yeah. Okay. I'm almost caught up. I'm almost caught up with the chat, and now my SEM image is caught up with me. we are looking at some cool San Francisco Bay stuff. Well, you know, it could still get holes burnt into it if you hold the beam on it long enough, even if it's sputter coated. The gold coating is really, really like, it's only a couple of angstroms thick, I think. We don't sputter coat for very long. I only put it in there like, it's probably 1 to 2 nanometers, or not even. So, you know, you could still burn a hole in that if you tried, I think. If we turned the beam intensity way up and just left it there for a while. So, Paralia colony. This is a diatom known as Paralia. I like to think of them as little poker chip stacks, as opposed to the cookie stack that we see sometimes in the same samples from Pacific plankton, which are usually referred to as Ellerbeckia, but they do also look a little bit like a cookie stack. That is a Thalassocyra on its side. That, I think, is a Meliscyra on its side. They're usually on their sides. And let's see. Pleurocyra, a Rhizoselenia, a Datylum. These are Thalassocyra up here. I've gotten a lot better at identifying some of the big round things, which is sometimes a challenge for me in marine samples, because there's a lot of them, and they're not ones that occur in freshwater, which is actually where my specialization is. So here's a long chain of Pseudonitzia. We saw a little chain of these before. We're still in live material stuff. In other words, it processed this just by rinsing it a few times. So I filled it with water, drained the water, filled the water, drained the water, to get rid of the salt. So, and that's because early on we tried doing this without doing that, and what happened was salt crystals grew on the stage. So as cool as that is, everything that's going to get in my way when I'm trying to look at whatever it is, a diatom or whatever else, is something I want to try to get rid of in pre-processing. So this little guy is actually one I know, because I think that is just a Navicula, which is a diatom type that we see in freshwater systems. This is a benthic diatom. You can see how different they are. It has very distinct raphe running down the middle of the valve, which is a sort of split in the valve face right here. And then these little rows of areolae, which are not dissimilar from things we see in other diatoms. But the ones in Navicula and all the ones in the Bacteriophyceae have different shapes. So this one has sort of what we call lineolate striae that are in little rows or slits, right? So here's the individual striae, are these little slit structures right here, and then stacks of them together, usually defined by costi that are between them. Costi is just a Latin word. It means rib. So it's like a rib of silica that's in between them. And if we were looking at the inside of the diatom, it would be much more clear. But we're looking at the outside of our diatom. So we can just see the raphe structure. These are these long slits that they use to crawl around. So the benthic diatoms are kind of cool because they're actually motile, many of them. And this little guy is definitely motile. So it would use that raphe to crawl around on the surface of whatever it was attached to. It's one way for us to very easily tell. So sometimes I look at diatoms that are millions of years old. That diatom is always going to be benthic because it has a raphe, and the raphe is only useful if it's attached to something. So as an example, we can use that to go, oh, this thing must have lived on the bottom, because there's no reason to have a raphe if you don't live on the bottom, right? So we can use a little bit of their structure to tell us something about how they lived, even though the organisms can be long dead, right? So it might be millions of years old, and I could still go, that one lives in shallow water, this one lives in deep water, based on the structures of their valves. So one of the things that's really kind of nice about diatoms is that in some cases we don't even need to know what the species is to figure out more or less how they live. It helps. The more information you have at the higher, the highest level possible, the more information you can then sort of determine from how they lived. But it's not necessary if you're just trying to figure out, is it deep or shallow water, or, for example, does this thing live in the ocean or does it live in fresh water? We can usually figure those things out based on the sort of genus level characterizations. So I gave some examples of diatoms that lived in colonies, for example, and the colonial organisms sometimes give us some clue about how a diatom lived as well. So this is a cyclotella. Cyclotella more commonly occur in freshwater than in marine systems. They're usually a little bit smaller than the marine plankton. They've got a series of mantle photoportula, which are these little holes that go around the outside edge. And they use those usually to sort of create a little parachute of EPS that sort of sticks out the holes and causes the diatom to settle through the water more slowly. So a sort of a baffle that they build out of organic material. And then these are the central photoportula here that are rimming around the outside of this sort of upward deflected part of the diatom valve face. And what you can see in this diatom, which is kind of cool, is that it has what's called a transverse undulation. In other words, on the valve face, there's sort of a kink in it, or a bend in it. And so there's a sort of depressed region and an elevated region. And this sort of brainy looking material that's here, this sort of colliculate structure that's on the valve face, is characteristic of diatoms that belong to the group of Cyclotella known as Cyclotella striata. So I don't know if this is actually striata or if it's just like cousins of striata, but that's where I would start with when I start to see this sort of colliculate structure that's got a deflection across the valve, an inflection like this across the valve face. And then it has all the other characteristic components of Cyclotella. So Cyclotella is usually determined by a ring of mantle photoportula. Somewhere around the outside edge here, there should also be a labiate process. Somewhere in this ring or near the ring of mantle photoportula, there's going to be like a larger hole than usual typically. And then we can use that to dump it into the Cyclotella group. And then we know that it belongs in the genus Cyclotella. Typically, Cyclotella don't have any areolae on the valve face. They have a sort of solid plate, or in this case, it's a sort of colliculate structure on the valve face. And then the only holes that they typically have on the valve face themselves are central photoportula, which is how I knew what these were, even though I can't see the strutted processes, which are on the other side. So this is just one valve in valve view. In other words, we're looking down on it from, the valve face, and then the girdle bands here on the outside suggest that it's attached to another diatom valve on the other side, meaning it's probably a complete frustual, although I can't tell for sure. So this is a pretty cool image. I'm just going to go ahead and snap that, and then maybe I can try to catch up with Chad again before I have to get back to another one of these pictures. Okay. Oh boy. Let's see. Do I actually measure the size of the coating? No, I figure out the deposition rate, and I calculated the thickness. So I don't know. Yeah, they don't measure it. They probably just calculate it, because you can get the deposition rate for the sputter coater, Frecht, and it will tell you if you put it under this sort of amp and you leave it in for this long, you get this sort of a thickness. And then I just sort of guesstimated that it took me about I think I leave it in for 1.5 minutes usually. So that's typically how they get that value. They don't actually measure it. But somewhere the people who made the instrument measured it, deposition rates or something. I don't know. They must have calculated it. So let's see. Sounds like an approximation. Yeah, well, deposition rates are sort of an approximation. But, you know, let's see. Big round things sound so scientific. Yeah, that's the way I talk. You know, I don't need to say everything sciencey like. Are these the same diatoms as last time? No. These are different samples. These ones I didn't process, but they are from the same location in XU. And I do have some samples, another sample from more recently collected that Pacific sent me that arrived a little bit after Christmas. And I processed those on Wednesday, and I've been trying to get them ready for today. Yeah, same sample. So we looked at a Pinularia time-lapse last night. That's true. I watched a little bit of Dell's. I watched most of Dell's stream, actually, before I fell asleep. Let's see. Let's see. Look like brains, yeah. Any cool adaptations for diatoms in the abyssopelagic zones? Not typically, because, Alan, diatoms need light. There are some weird diatoms that can switch between autotrophic and heterotrophic, but most of them require light. So once you get into these really dark conditions, they don't live very long. They usually are on their way to the bottom of the seafloor at that point, and they don't really have adaptations for it. Hopefully I answered the question about the black dots along the edge. I think there's a Mantophotoportula or valve-face photoportula, yeah. Yep. I'm trying to catch up. Sorry, I'm not going to make it. You need a scanning electron telescope? Do they have those? I know they have radio telescopes. I don't know about a scanning electron telescope. I feel like it'd be hard to like shoot the beam that long, that far, and keep it, in a beam, tight beam, for electrons. So this is Cyclotella striata, I think. Oh, I took a picture of one of these already. Okay. And we saw some of those last time when we were clearly, because I took a picture of it. So let's see. Oh, I took that at beam intensity 10. Why would I do that? I was just in a rush, I think. So I keep thinking one of these times I'm going to see something. So that's a sponge spicule. And I saw some radiolarian pieces. And I keep thinking one of these times we'll find something that's like a dinoflagellate, but we never do. Either they're always crushed or something. I don't know. We never find any good dinoflagellates, but they're definitely common in the samples when Pacific Plankton's looking at them in the light microscope. So it could also be that they're lightweight and they float. Their body maybe floats, and so when I vacuum off the salt water, it could be that I'm vacuuming off all the dinoflagellates as well. What I really should be doing is using a filter, probably, and filter paper. But I don't have a filter pump, which is what you would need. And because I just don't do that sort of thing very frequently. I mean, I could get one, but it seems like it's not something that I really use in my lab. So if I got it, would just be sort of like for selfish purposes of doing things on stream. Although it might help some of the other people who work here at my university, because they use, they look at marine stuff. This looks like maybe it's a Eucampia chain. I was hoping we'd find some of these. They're so lightly silicified. It looks like they're already starting to kind of break down a bit. But you can see it's got like one slightly longer and one slightly shorter piece that are connected together. And as a result, then it creates this sort of ring structure. And you can see how completely lightly silicified they actually are. And here I'm going to play around with my settings a bit, because the girdles and these little horns that are on here have a bunch of little holes on them. And anytime I see something with a bunch of little holes like this, I want to get my SEM's focus perfect, because that's what it's good for. So here we're looking at a 1 micron image, and the scale bars at the bottom is 1 micron. It's actually 4 microns across our field of view. But I wanted to use this to kind of showcase the beam intensity issue. So this is as good as my focus can get with beam intensity 10 at this resolution. If I switch to 7, you can see the difference between them, right? How much better the image resolution is at 7 than it is at 10. Now we can resolve all these holes. But as I mentioned, it always looks a little bit grainier, but at least now everything is nice and clear. And if I wanted to zoom in a bit, oops. First I need to get the focus back perfect. If I wanted to zoom in a bit now, I could, because I've lowered my beam intensity. So the scale bar at the bottom says 200 nanometers, give you a sense of how small we are. And again, now we've reached the limit of my ability to focus that image, right? So I can go all the way around from in focus to out of focus and never really get it any better than that. And there's 2 ways to handle that. If I'm going to take a picture, one is, so you can see I'm too close. I could lower my beam intensity again, right? There's nothing stopping me from doing that. And then I could go back to trying to focus. Again, it's sort of out the limit of it. So right now we're at 215,000 times. Probably I'm not going to be able to resolve something very clearly like that. So the best thing to do would just be back off a little bit, right? And then we're at beam intensity 5. So if I slow the beam down, we get a fairly decent photo of it. I think this is still a little grainy. I could lower my beam intensity and change my brightness and contrast again, try to get a little bit more perfect. But what I wanted to do while I was down here in this sort of tiny focal height is tweak my stigmation, because that's another thing I can do to kind of improve images. When I get my beam intensity down to 5 and I'm sort of at this limit, is try to see if I can put some glasses on my SEM and correct that image a little. And it is totally possible to do that. I have these really fine controls that I can use for basically putting glasses on my SEM and adjusting that beam on a really fine scale, like so, to give us a nice high resolution image. Now I've got the beam corrected just a little, and so that's a nice view. It's a little dark. I can do this. And then probably don't need to be beam intensity 5 for out here. And we're just looking at this little tiny piece of this Eucampia. And as I zoom out, you can see the entire cell, right? So this is one diatom cell right here, and the next, and the next. So we're just looking at little tiny pieces of it. And you can see this thing's actually fallen apart or collapsed on itself a bit. And this sort of middle component of the cell wall is now broken off, or maybe it's just folded down onto the other side. But from out here, basically I can just turn my speed down a bit and get a nice clean image. So with all of the detail very clearly highlighted on the valve structure, right? In here, right? You can see all the detail of those little tiny holes in that structure. So I'm going to even maybe bump the speed down to 8 so I can get a clean photo, and maybe I can actually catch up on chat. Okay. An olfactory telescope. Let's see. Can I share it here via Reddit link? Sure. You can put whatever you like in the channel, Del. You got one of those swords. How does one go about coloring these images? So normally what I do is I put it into Adobe Lightroom, and you can usually affect the shadow, the midtone, and the highlights separately, and I can colorize each one of those as different colors. And so that gives me some pretty good colorization that doesn't just look flat, right? So if I just made them all red, then it would just look like I took the black and white image and put a red filter over it. So what I usually do is go in, set each one of those in specific color ranges with different luminance values, and tweak them the way that I want. And then, as I mentioned, I'm using Procreate now as well. So I start with Lightroom, I dump it into Procreate, and then I might stick it back into Lightroom after I finished it with Procreate. And in Procreate, I can actually paint colors in and do like color dodges, or I could go in and sort of fix the image a little bit more. I can add a little bit more color. Yeah, Pandemic Watch says sputter deposition is extremely precise. See? Hopefully that convinced you, Frecht. Let's see. Diatoms are autotrophs. They can switch. Some of them can switch to be heterotrophic. They're very uncommon, but there's at least 3 or 4 species that can switch between autotrophic to heterotrophic. So just keep that in mind. It's great that you decide to stream and multitask with chat. Yeah, I'm sorry, it's difficult for me to always keep up with everything. I try. And I was doing text-to-speech, but I felt like I couldn't hear while people were talking in my ear. So I couldn't talk, basically, when people were talking. It was very challenging. So let's see. Perforate. Focus. Yeah, okay, good. Well, you all see what I was doing, hopefully. We're in the ultraviolet length, the IR wavelengths, tinier than the wavelengths of light. There's no light in the SEM, I should point out. The only light that gets into the SEM is actually from, let's see, there's this infrared camera that's looking into the chamber where I've replaced my picture right now, which shows you the different stubs that are in there. And it's always on. I can turn that off, but it's not actually producing any of the image that you see. It's producing that image in that camera right there. It's just a little webcam, basically, that looks in there. When we use the elemental analyzer, I actually have to turn that off because it interferes with the energy spectra that's given off of the sample. So just as an example. But there's no light inside the chamber otherwise. So everything that you're seeing is built by electrons. And that's the power of a scanning electron microscope, is that the wavelengths are so small of an electron. It's like half of a nanometer or something. No, it's at the angstrom scale. Half of an angstrom or something for an electron wavelength. Then as a result, basically, you can image stuff a little bit better, right? There's really small stuff. So let's see. Back into the blue-green. Yeah, I'm looking at just that little tiny bit. I was just trying to get tweak my focus. I can go back and image something at really small size if you'd like me to. Let's see. EDEX. Yeah. I have an EDEX. It's mounted to the scanning electron microscope, but the problem is that everything we're looking at is basically silica. For diatoms, there's not going to be a lot of difference. These are gold coated, so you get a little bit of the gold spectra, then we get silica and oxygen, and then there's some trash on the stage, so we'll get some carbon, and we might get some other things, but basically we wouldn't get a whole lot else with respect to the EDEX. But you can get chemical composition out. So, yeah. Okay, so I did catch up with that. Now I can, let's see, I can briefly jump over to see all the follows that I missed. Jesus, I'm sure there was a ton. I'm sorry about that. And yeah, here it is. I can catch up. I promise. Let's see. We got Garden Outside from an hour ago. Our raid from Last Miles an hour ago. Funk Dev from an hour ago. Bali Baba, who asked some questions in chat, and Maddie, who asked some questions in chat that followed about an hour ago. Feebach, Epic Catado, Adeja, Vid Valvoler. Sorry, that's a tough one. Pin in 84, Econ Greg, thank you for a follow. I'll catch up with you later with a follow back. Dendo Rando, Sargo Centron. We had the gift subscription from Samsung TV and Morocco and JMSC404. That's a big number of followers. I should mention that we're over 900 followers right now. And I'm super excited to be able to share the SCM with so many people who seem interested in it. You can see the really cool structure of the Eucampia on the valve faces right here. And, you know, because we're looking at it in girdle view, you can see here's one of those valve face structures. You can just see them basically spaced out in between each one of these cells. So there's a valve face, a valve face, a valve face, right? And hopefully we can find one that's kind of looking at us from the valve face. Another thing that's really cool about this image, I didn't notice because I was busy looking at the valve faces and stuff, was, let's see, can I get over to that? Can you move over a little? Oh, yeah. Right here, there's been a detachment of one of those two sets of spines, and this one's kind of bent, and you can see the pieces that connect right here. This one's bent up, so it's like pointed right at us, and you can see the actual structure of the part that's bent up at us, right? So there's connecting spines. You can see a little wispy structure standing off the edge of that other part where it's broken free. And then this one, which is like pointed right at us. So if we were looking at the valve face, we'd be able to see those little horns. It's got this really cool little structure on it, like poker chip structures that probably match against the ones that are over here and help to hold the valves together. So that's super cool. Oh, somebody asked about the SEM. What am I looking at? Angry Carrot. This is a scanning electron microscope view of a diatom from San Francisco Bay. It's the genus Eucampia, and one of many diatoms that we've looked at in the stream today. So hopefully that helps. Somebody gave you a link there for information on diatoms. If you don't know what a diatom is, they're a type of algae. Their skeleton, their cell wall is made out of silica. And so that part preserves, and we can look at it easily in the scanning electron microscope. Yeah, we're getting close to the 1,000 followers. We're creeping up on it. And we got a new follow from Sylvan Matz, who also asked some questions earlier. So thank you, Sylvan. Sarah says, I have lizards that are implanted with cortestosterone. I will show pieces of them on the SEM soon. Yeah. So I think we're going to try to do that this week, next week. Sarah's going to come down from her lab upstairs, and I guess we're going to dissect a lizard live on the screen, and then put the samples into the sputter coder, and we'll look at some lizard pieces on the SEM. I'm not a lizard specialist, so we're going to really depend on Sarah to help us with that. Both the cutting, because I'm not going to cut up a lizard, and also the actual like parts. But once we have them separated from the lizards, I think the lizards are already dead, so don't get yourself too worked up, and probably mummified. And we're going to put them in the sputter coder, and then we'll bring them in and put them on the SEM. So I don't know what all we're going to look at, but I'm sure it's going to be exciting. I've got a little document camera that we can use to image all of the stuff that we're doing, like so you could see the actual sort of dissection part, which I think would be really cool. As long as it's not me doing it, and I can always leave if I start to feel nauseous. I'm not a person who likes to cut things that we're living. If it's diatoms, I'm fine with it. But you know, they're algae, and they're clones. So everyone that we see is just a clone. Okay, so let's go look at this thing real closely for a second, seeing how we have it here, and it just happens to be facing the camera. Oh yeah, you can see that structure really well. And it's not below our threshold for being able to resolve things clearly. So if we get in and look at it really good, like this, you get a really good sense of the structure, right? It's got little holes. Everything with the diatoms have little holes, right? But it's like a poker chip, little poker chips with holes, and presumably they probably exude some EPS out those holes to help hold them together. So I'm just trying to get the focus a little bit tighter, which is basically what I'm always doing when I start squinting at the screen. I think right there is good. And I don't necessarily want to be quite this close. I want a little bit of context for what we're looking at. So our scale bar is just 2 microns, and you can see a lot of those little cool structures that we imaged before on the texture on the valve face, the little areoles, on these sort of horn structures that are on these Eucampia. So see if I can get that just a little bit cleaner. I don't want to image it and then have it be out of focus, especially when we had such a nice shot of it. It's hard because we're in so close that part of it's always going to be out of focus, I think, but that looks okay to me. And we'll just take a quick photo of that. Let's see. Yeah, we can actually do the dissections on screen. It's going to be a little crazy, but no, they can see what you're doing. Clone lives don't matter? Yeah. That's why you can shoot stormtroopers, right? They just clones. That's why you want to come to the dark side. We've got clones. Okay. I'm working on photos, yeah. Your daily dose of high-quality diatom footage. Hi, Dr. Javasaurus. Look at this. I might actually be able to get the shout-out to you myself. Doctor, let's see if I can beat everybody. I did it. You should check out Dr. Javasaurus, right? Let's see. You hope I'm doing okay. If I haven't seen you yet, Happy New Year. Happy New Year to you. And may 2020 bring you as much exciting science and discoveries to last a lifetime. Thank you. Also, we got a nice follow from Walnut Steak. That sounds delicious. Your science, your Twitch channel has very little to do with your... Okay, we'll catch you later, Econ Greg. Thank you for hanging out with us today. Your Twitch channel has very little to do with scientific aspirations, though. You know, it's okay. Sometimes I just have my daughter streaming Minecraft. Whatever. You know, it doesn't always have to be the thing you want to become. Although I really haven't done any like home streams in like a month and a half or something. So it's coming up. I promise I'm going to do one sometime here. From one scientist to another, do you have any advice on how to get back into science and academia? I don't know why, but my former research group hasn't replied to any of my messages in 2 years. I don't know. I didn't leave academia, so I don't really know. And I don't understand why people wouldn't answer your emails either. Yeah, Code Monkey's no fun. I'd like to say being stuck in front of a computer is no fun, except for I'm in front of a computer right now, and this is fun. So, um, uh, yeah, I don't know. Academia is a weird place. Sometimes people are just jerks, and there's no way around it. Um, but I guess it depends on the field you're studying, maybe, and the kind of people that you work with. So, um, I know diatom people are pretty cool. So for me, it probably would be easy. And I'd like to encourage people, if they're interested in doing stuff, to just do whatever it is they want. So I'm just going to call this a horn tip. I don't know what else to call it. I don't know the language of the marine diatoms well enough, their body parts to get a grasp on it. But I would like to say thank you for the channel visit and the well wishes for 2021, and same to you, especially if you're looking at getting back into academia. Um, you know, here's to somebody out there having some common sense and treating people like human beings. Because why not? I don't understand why not. Sorry, I saw this over here and was trying to figure out what the heck it was. Because every little thing I see that's a diatom makes me wonder, like, what the heck is that thing? And I'm pretty sure that's a diatom. And I still don't know what it is. It's very small, which is atypical for a lot of the marine diatoms, but these two little holes are very diatom-like, and all these little holes are pretty diatom-like. So I'm going to go with it's a diatom. I'm going to take like a quick picture of that one. We'll just do like a 1-minute snap. I have no idea what that is. Let's see. I've been shoved to the pure software development role in a big pharma company where I actually wanted to do what I was hired for, which is bioinformatics. I think bioinformatics is a big field. You ought to be able to get back into that. I think there's a room for that. There's growth in that field. So you like learning free of the chains of academia. Yeah. So for kind of like academia gives you a lot of like scheduling freedom, which is the part that I like about it. I'm able to stream. I'm able to do field work occasionally, hang out with my family when I want. It pays okay. So probably not as good as a code monkey for a pharmaceutical company, though. Costi Acelli. I don't think that they're Acelli for those, but maybe they are. Pacific, because I guess they could be Costate Acelli. They don't really look like Acelli in the sense that they have like ridges between them, but I guess that's the Costi part. You refurbish Game Boys? I mean, whatever. If it looks like a diatom and it quacks like a diatom, it's probably a diatom. I do art, music, and weird news, and meditation, and OBS visuals, and tutorials, and whatever, yeah. Getting a PhD seems easy. Anything that follows is not so much. That's probably an accurate way of thinking about it. We seem to have endless amounts of money to fund students to become PhD, and in some level it's irresponsible because we don't always know how to give them jobs once they're out into the market with that PhD. It's like you become over specialized, and then it's hard to find like a role for yourself, especially if you're, not capable of getting a job in the actual academia. And it's a challenge. So I should say for 6 years I was a postdoc, and before I got my job as a professor. So it's challenging, and I'm with you on that. And it's not like I had a bad record. It's just I came out of my PhD into a pretty crappy economy, which is sort of where we are now. Only now there's a bigger reason for it. This little guy right here is a Silica Flagellate. You can see the silica structure is this sort of ring shape, right, with spines sticking off of it. And then it's like a cage, right? So we're just looking at half of it or whatever. The internal part is occluded by these clays. Probably the biological material that belonged in it, because we didn't, as I mentioned, process these at all. So I will zoom back out. We see these squishy things on the screen. I don't know what this squishy thing is. Oh, maybe that's a piece of sand. It's another diatom. Well, I'm kind of excited we got a Eucampia. We haven't seen those before from this material. And been seeing them quite a bit on Pacific Plankton Stream. And I thought maybe that we would see some in the sample 8, which is the other one that's here that we haven't even gotten to yet, because I've been screwing around on this one. So let's jump over to one of those. We'll start with the live material, or the unprocessed material from 8, which was collected at the end of December, from last year, all of a couple of weeks ago, I think, or less. And here's a tintinid right here. This tintinid's made its skeleton, or its home right here, its lorica, out of bits and pieces of whatever's around. And sometimes diatoms are what's around. And there's an example of it. You see this little piece of a diatom right there in the skeleton of this thing, other organism. And I think they also eat diatoms, but I don't think they ate it and then stuck it onto the skeleton. I think it was a dead part that got attached, agglutinated to the outside of their test, of their lorica. So pretty cool. Here's another one of these Cyclotella striata looking things. This one's standing up on its edge a little bit. Nice clean view of it. You can see the transverse undulation really well right there. You can see how it kind of comes across. So we haven't looked at this sample at all before, and I start off here in the organic rich version where we didn't process it. Here's a big stack of something. I'm not sure what that is. I mean, I know it's a diatom. That part, there's no question. That is a diatom colony for sure. It doesn't look like, it doesn't have the structure of a Paralia. And it also does not have the structure of a Ellerbeckia, I don't think. See if we can get a view of the valve face. So for Ellerbeckia, typically you see like a poker chip structure here, and we don't see that either. So this is something that is making long stacks of diatoms. That's different. And so I'm going to guess that if I looked over into the channel, Pacific Plankton will be telling me, get a picture, because I'm going to, trust me. This one's not one that we've seen before on the stream, and not one that I've imaged before. It's nice and tight. You can see there's a whole bunch of clay on the outside of the valve because it hasn't been processed. So we'll just do this. Beam intensity is 7, which is good. What is all this? It's just the way that it looks when you get a little bit distant from it, I guess. Lepidos cylindricus, maybe? I think that's probably what she's telling you in chat. We'll figure it out. One thing is we get the SEMs, and then there's no way it can hide from us. Okay. It's not an Ellerbeckia, though. I know it's not, because the valve face is wrong. Yeah. Okay. Sorry, I didn't mean to abandon this conversation about PhDs and stuff, but... I feel like I've missed the thread a little bit on that conversation. So I'm just going to let it go. Don't give up. I don't understand most of what's here, but I slowly become familiar with things where I visually recognize things after a while. So at my age, I can still pick stuff up. Age is just a number. If you want it, you'll find a way. I agree with that statement. Age is just a number. Don't worry about it. Focus on what you want and keep at it, I guess. I've got some new follows that I should mention while I have a chance. Time Traveler 9791. Are you coming back in time from 9791? And you're watching SEM streams? It must be very comical. Testudy. Testundi. I'm going to work on it. Zadkiel 2 and OG Marathon. Thank you guys for your follows. Oh yeah, and OG Marathon sent out a squad chat for my fellow streamers who use microscopes, including some of my moderators here in the channel, Del Maximum and Pacific Plankton. Two great streamers you can watch. You don't need a PhD to do microscope work. In fact, none of the other people in that list that I know of, except for maybe Spider ID, has a PhD. But they all are very entertaining and have very pretty images on their microscopes. So you should definitely check them out. A Tiny World usually does like water bears, and she's been doing podcasts, and I've been interviewed on her, which I think is going to get aired soon on her podcast. Pacific Plankton sent me these samples. So she streams on Monday nights and Thursday nights at midnight till 2, typically. Delmax is not on Tuesday or Thursday, but he's on most of the other days. And he does microscope streaming and games. Open Set, who usually comes in for a visit at some point during my streams, is another streamer who plays synthesizer at the same time as he does microscope work, so he gets his own music in the background, and then he's got a bunch of really cool visual components to his streams. Vizaria is actually a singer who does a little bit of microscope stuff now and then. Just a beautiful voice, though, and you should definitely check her out. And then I added Spider ID to our list. So Spider ID streams from Europe, and so he's on usually in the mornings, and he just looks at spiders in a stereo microscope. I have the same stereo microscope as Spider ID, so I need to hit cancel on that. I want to save it. I want to save it as 8. And I need to make a new folder. Because we are in a different sample finally. Okay, something cool and new, and probably not Ellerbeckia. Yeah, okay. Zoom out, speed, beam intensity. Now we can look around a little bit. So these things right here are Ditilum. One of the reasons that we have been looking at things without processing first is so that we can see things in their life position. You can actually see the girdle bands of the Ditilum here, which are almost always disappear the moment we put any kind of nitric acid or anything in the sample. But you can see that how they were attached in life. They look like a little triangular shaped marshmallow on a stick. Really neat looking. And we saw a bunch of them that looked like they were sort of encysted in these samples somehow. When last Pacific Plankton was on. And I think that was Monday. And here's some more of those Pseudonitzia, which had been pervasive in her samples for a while. This little guy here is a Coscinodiscus perforatus, which we've seen a bunch on this stream, because it's one of these really cool looking Coscinodiscus diatoms. And I actually learned that one to species as a result. Another thing that's kind of cool is, see that little thing there? And that big thing there? I think they're both diatoms. I think these little guys are diatoms. It's that little thing we saw before, right? With the little holes on the valve face. There's a diatom. This one's only about maybe 5 microns across. And it's probably something like mini discus or something. Here's another one right here, right? These little teeny guys. Oh, maybe it's a Thalassicyra. I'm not seeing any structures on the margins, though. So it's something else. So it's got little holes on the valve faces. They're probably valve face Fortiportula. And then here's 2 of them. Each of them are about 5 microns wide. That's the whole diatom. And it's next to this giant Coscinodiscus, right? That's also a single-celled diatom right there. And they belong in the same, like, upper level construction. In diatom taxonomy, they would all belong to Coscinodiscophacia. And probably they all belong in the same subclass for diatoms, which is kind of cool. Okay, yeah, and the mucilage probably was the thing that was holding them together in life. It's gone now. I'm not sure what this thing is. It looks like a Chitoceras with the spines broken off. Oh, nope, it's got cool structures on the valve face. Huh. Another new thing. I always get excited when we find something new. Not that there's anything wrong with the old things that we see, but when we find new things, it's really neat. Especially this guy's got really cool structure. So I'm going to beam intensity 7 so we could actually see them. Crazy little structures. The scale bar down there is at 500 nanometers, by the way, so you're wondering how closely zoomed in we are. Currently, we are 118,000 times magnification. Good luck finding anything like that on Twitch. That's not this channel. Just going to put the whole thing in our field of view. I think I can rotate that. I want like 320. Where'd you go? Oh. Didn't do its calculations perfectly. Almost lost it. It's just because we're so zoomed in. This little guy is tiny. Still could go around a little farther. Come back, football-shaped thing. Here we go. And now I need to focus again. To be just perfect focus. Like so. And then I'll just zoom out a little bit and we will ramp up the resolution by slowing the beam down. It's looking good. Let's see how that does. I can come back and see the chat. Dr. Cheese Weasel, thank you for the follow. Also, Satin Nature, thank you for the follow. Pretty cool. Cheese Weasel, a cheese weasel doctor. That is really cool name. Let's see. Oh. OG Marathon says, I am stoked, dude. I'm also working in imaging C. elegans. I think that's Catastris elegans, maybe? Dope to see the stream and streams like it. Welcome in. Okay. Let's see. Where am I? Looks like a skewer. You dip in a chocolate fountain. Yeah. That's true. Those Titillum look like that, don't they? You put a little triangle-shaped marshmallow on a skewer, put it in a chocolate fountain, eat chocolate diatoms. I don't know what I didn't take a picture of something you probably wanted me to, Pacific. I'll have to come back for it. We can also ask Anna. She would know. Can you imagine telling someone you are the mucilage that keeps us friends together? That's how I was. It was like this sort of mucilage that held all my friends together. Still am, I think. Are these just the skeletons of diatoms? Yes, because the skeleton part is the only part we can really see very easily. The cell wall is the silica frustule. In a vacuum, these have been dried, and so all the organic matter that might be present in the sample is probably like contracted into a little slimy, like, you know, internal blob of whatever in the valve. So everything's dead, but even the organic parts are probably mostly missing from there. Yep. Satin Nature. I have a compound microscope. Actually, I've got like 8 of them, but only like 1 at home. Oh, that's true. I only got 2 at home, but 1 I own and 1's from my lab. So, yep, that price is about right. A little out of everybody's price range. It's out of my home price range, but not out of my lab's price range. I'm trying to find it in a book. Yeah. How far does it magnify? Yeah, we talked about it a little bit before. I can get up to about 150,000 times magnification, and then it starts to get a little blurry. So right now we're at 40,000 times magnification. And I embarrassingly have to use unknown diatom for the name for this one, and it's 2 in a row. I feel like we ought to look at some diatoms that I do know so I could stop putting unknown diatom in as the descriptor. You know, for the sake of my fragile ego or something, I guess. Oh, it's all right. I'm not afraid to not know things. I don't know what that is. It's a weird looking blob. Maybe a foram. Looks like a foram blob. So tintinid, diatoms, those are all Pseudonitzia. There's this big Cossinodiscus. There's another tintinid. So some tintinids. This is diatom right here. That's the Thalassocyra. This is Actinopticus. Not sure what this thing is. A fragment of something. Sorry, I'm just kind of sporadically jumping around. This looks like it used to be something. Got squished in the vacuum. Sorry thing, whatever you were. Ditilum. There's some sort of structure up here. Chitoceras. That's a diatom. This is a Cossinodiscus. We saw these with his really ornate sort of star-shaped pores on the valve face. When we get really zoomed in, you can see them. Also, when they dissolve a little bit, they're easier to see that structure. Chitoceras, that's a Thalassocyra. I made some light microscope slides of these diatoms, by the way, and I'm getting ready to send them back to Pacific Plankton. I've got another set of them that are kind of cooking right now on the slide warmer. That is a weird structure on the side of that ditilum. I'm wondering if that's a different species than the ones we've saw before, or if it just looks kind of weird. So it's got this like very ridged structure to it. This one doesn't look quite so ridged. Chitoceras. There's a little turd. Now it's a poop stream. Oh well. There's a tintinid. They look like little Christmas tree lights, right? Outdoor Christmas lights for people who celebrate Christmas or forced to look at their neighbor's lights. And little fragments of diatoms and other pieces of other things are agglutinated into the skeletal material right there. Those look cool. Those look cool. The valve faces are like pointed towards each other because of the way that or they're both pointed up sort of because of the way that the girdle band collapsed between them. It's kind of neat. Let's zoom in and take a look at that. And I can get a picture, because that's what I do here. Is good. It's just a little crooked. So 3... Go back to 0 maybe. Just needs a little bit less. 350. So I'm trying to guess the degrees. Here we go. Looks good. That is a cool look at the ditilum. And since we rotated it, I'm going to come back in and take a look and make sure that our focus isn't too far off. kind of hard to be too good because a little bit of everything's in and out of focus at the current way it's currently facing, because our depth of focus is not that great. Our depth of focus right now is only about 18 microns, and the diatom is way bigger than 18 microns across probably. So like the spine tip will be, the Rimoportula tips will be out of focus, but parts of it will be in focus. We'll just have to settle with it looking artsy, you know. Sometimes you have to like just deal with it that it's artsy. So you can resolve those actual little pores very clearly when I change the beam intensity down to 7. And then I can just snap that photo. I'm going to come back to chat, see how things are going. How are things going over here? Yours cost $75. Well, that's a deal. That's a good deal, user plus number. On a Black Friday sale. Can you stream from it? You going to stream from your microscope, user plus? Atoms are too small for that kind of microscope. Yes, we're not down to the atomic level for sure. We can get down to nanometers. Hundreds of nanometers for a photo usually. So I find diatoms really cool. I don't know a lot about them. Are they part of the meiofauna? Well, they're flora, first of all. Like tardigrades and rotifers, they're smaller than those. They get eaten by tardigrades and rotifers. So they're in the... they range from what's considered ultraplankton to microplankton, I think. There might be some that are picoplankton. Some in this slide that are only like 5 microns long. I forget where the boundary for picoplankton is. If it's like 2 microns? 2 microns maybe. If I go to the maximum zoom, I might be able to see your bank balance. Oh, is it in the 100,000s times? Or it's just really small? Let's see. I do pictures. We talk science. We do a little bit of taxonomy now and then. Occasionally I like to do interviews with scientists. I just haven't had many people that have volunteered to be interviewed by me. And I haven't pushed very hard on it, but I will. I'm going to make it an agenda for this, for the new year, is to have a few more science streamers come in and talk about their research, and we'll try to do it in a way that everybody's grandmother can understand. You know. Looks like autumn crafting at my son's school. I don't know what autumn crafting means. Like putting leaves together or something? I started courses to work to protect environmental stuff, and I kind of fell in love and bought a microscope. That's what I study. But like knowledge, so learning here and there, basic botanic biology. So I have a lot of questions. That's all right. We love questions. I'm here to answer questions in part, right? It's a spaceship and a delicious snack. I mean, who doesn't want a spaceship that's also a delicious snack? I love this cooking show. Hey, Django Macro, hello. I request for both colorized versions. Okay. I will try to do it. A bow tie pasta. A little bit like that. Hey, thank you, Sat Nature, for your subscription. I appreciate it. I should point out that I don't take any money from subscriptions or whatever. I pay taxes on it, and then I donate it back to my lab so that my student researchers can do work, and also we sort of replace the stuff that we spend on the stream. So I don't actually make money. Don't intend to make any money unless I start getting like, you know, thousands of subscribers. I guess then I'll make more money than I can spend in the lab. But I would really like to just use it as a resource for supporting students, and I view this as part of my job, sort of a different part of my job than usual, fun part. So can I use focus stacking? I've got a better plan. I could use focus stacking if I wanted to. Oh, it looks like the tip of that got messed up. Is that for real? Oh no, it's just a messed up tip. I thought maybe it got like glitched, but it didn't. Okay. I could do focus stacking. I could also just back off a little from the sample and take the same picture, and parts of it, you know, as the farther I get away from the material, the more of it will be in focus at once. So I could get a sense of roughly how much of it I wanted in focus, and then I could just back off a little bit. This is the species Diatoms, both vowels. So I could get everything in focus at once, just by moving out a little bit. You know, I don't think I would lose a lot of resolution for what I'm trying to image here, but I actually kind of like to have things a little out of focus. I just kind of like the artsy look to it. If I was doing a science, like if I was imaging this for an actual publication, I probably would try to get everything in focus. But because it's for fun and for art, I'm going to turn it into an Instagram picture and post it to Instagram and potentially, you know, whatever, Facebook, anywhere else. So for those purposes, I actually am okay with it just looking kind of artsy, right? It's okay for it to be artsy if I'm actually using it for art purposes. And you know, if I was focused on a particular part of it, you know, I wanted to get something in focus or more focused, then I probably would make some adjustments. But because I'm just kind of imaging it for my own sake and for viewers, it's okay for it to be, you know, artsy, as I said. Here's a skeletonema. We saw a bunch of really well developed skeletonema before. This one's got a break in its little Lord of the Rings cage, so you could actually see in. I was hoping one of these times we'd find one with a valve face sticking up at us, but they're so small relative to everything else that we see in the samples. I probably always overlook them. You know, you've got to... If I was looking, like, if I spent the whole stream looking for skeletonema, we probably could get some really good ones, but I don't usually do that. I'm just kind of like surfing around from a distance. There's a radiolarian to try to get some sort of cool images here or there, but you can see like I miss a bunch of stuff, like these little tiny things. What is that? Probably a Thalassiocera, a little tiny Thalassiocera that's hiding underneath there. Like, there's a lot of stuff that's down in this sort of size range that I just overlook, like here, because I'm zoomed out looking for something cool, and I overlook some of the really little things. I mean, I'm already looking at little things, but like they're even smaller, right? There's some really little diatoms in these samples, and so sometimes I'll catch one on the edge of something that we're imaging that's bigger, and zoom in on it. But a lot of times I just miss them. They're too small for me to catch. Oh, there's a Melisira, I think, valve face view of that one that we had the other day that was in girdle view. Yep. With these little weird projecty spine things that are star-shaped coming off of the valve face, and they're covered with junk right in the middle of the valve to ruin my picture, but around the edges they look nice. It's a Pleurocyra piece. It's a crazy valve face for a Chaetoceros. Interesting. Crazy spiny structure. It's not very well preserved. So these samples were collected, as I mentioned before, by Pacific Plankton. She collects from a pier using a plankton net off of an area that's adjacent to the Golden Gate Bridge. And so because she's collecting from basically the shoreline and just sticking out a little bit into the ocean, and there's a lot of waves, Sometimes you end up with some of the material from the bottom. So benthic material can get carried up and be temporarily suspended in the plankton, and so sometimes she gets a bit of that in the sample. So we end up with plankton species like these round ones. Most of those round ones that we see are plankton. That's Actinopticus, a little guy. Probably Syrians or something like that. I'm not sure. But then we also will see some benthic species occasionally show up in the material. And I think I just found a valve face view. It's an internal view of that stack that we saw, unfortunately covered with clay. Oh, that one does look like it's an Ellerbeckia. That's an Ellerbeckia-like structure on the inside of it. I don't know if it's the same one we saw before, Pacific, but that's an Ellerbeckia probably. That one's a cookie stack. There's another tintinid. I'm going to move back up and see that one. Occasionally I just like to check out the tintinids and see if they've got any diatoms in them, integrated into them. See, this one has a little piece of something down here, and maybe a little piece of a diatom in here. They just incorporate whatever's around into their skeletal structure. So that is part of the meiofauna. That's not a plankton, not a planktic organism. And we managed to go all the way to 315 already, and I still haven't even moved into the cleaned samples because I keep looking around thinking maybe I will find a dinoflagellate, but I still haven't. All this searching and I still haven't found a single dinoflagellate, so I'm guessing they just get vacuumed off when we clean out the salt water, which is unfortunate. It's a little chunky tintinid. Sometimes in these samples there'll be other things, like, I'm not sure what this used to be. It used to be something, and now it's dead. It's like a little trash bag that's been vacuum packed. There's nothing left of whatever it used to be. I have no idea what that could be. Other than it used to be something faunal, probably. And now it's gone. Alright, let's jump over to another sample. While we have time, we can still, here's another one of these big stacks. Some more of the similar things that we've seen. Immediately popping out at us. What was that long chain? What's this really long chain? A skeletonema. Yeah. For sure. With these long, sort of bone-like spines that are joined together in a very ornate fashion. Zoom. Look right in on the knuckled spines of that skeletonema. It looks like a trellis structure. I think Mama Bonbon said she thought it looked like a bracelet. But you can see there's a whole chain of them. A whole long chain of these skeletonema. Nice, well-preserved, perfect little skeletonema chain. We'll do one overview shot so I can come back to chat and see what's been going on. Why are there no bacteria in the picture? Yeah, usually I kill them with acid. Just call me Menzin, says hello. Hello. How are you? Putting skewers through leaves, add glue and glitter. Sounds cool. Yeah, everything in a vacuum. You're not gonna see any of that. I bought a camera to stream from my microscope, but I don't have your knowledge. Hey, you don't need to have my knowledge. It's fine. I'll show up and hang out in your chat probably and help out if you start streaming sooner or later. Moss and lichens, also tardigrades, other protists, plants. There's plenty of things that you can just look at. You don't need to be an expert. And part of it on Twitch is just the journey. I'm not a marine diatomist, but here I am looking at marine diatoms, right? So, you know, good enough. What was the structural perfection? Hexagonal one. I don't know. Sorry, I've forgotten that already. Hey, Billy Galaxy, how's it going? OG Marathon, this is an awesome stream. I gotta run, but it was so dope seeing this stuff going on. All right, OG Marathon, thank you for hanging out with us. Oh, it could have been an egg? Oh, maybe. Hi from Spain. Hello. Hello from Indiana. In the US. I'm still living. COVID hasn't gotten me yet. So, one day, could you keep the bacteria just to see? I don't know how I would see them, but I could try. I think you have to preserve them specially. You have to do some sort of critical point freezing to keep organic stuff from degrading with like a series of ethanol treatments. I need to figure out how to do it for some other work that I'm doing. We can either do that, or I think you can embed things with silica using special chemicals, which will cause the organic material to not degrade, and then we might be able to look at some of them. But it's a challenge to look at anything like soft in the SEM. It just always ends up getting destroyed by the vacuum, basically. So, walnut steak, hello. Let's see, J Hobo, thank you for the follow. Heavy Duty, thank you for the follow. And Miguel, Roland, 21, thank you for the follow. There's a skeletonema chain. Also, we're getting pretty close to the end of the stream. Skeletonema chain. And you know what that means? I need to find something really pretty real quick before it's too late. I've got maybe a half hour I can manage to sneak in still. What was that thing? What was that thing? I don't know. That's a question for Pacific Plankton. It's like a ring. That's not a diatom. It looks like a cruller. Like a donut. This is that thing that we saw before. It's not the valve face, but it's kind of close. See, it doesn't have the big ridges that I would expect for an Ellerbeckia, and it doesn't have the paralia margins. So there's something else in here. Secret type of diatom we haven't figured out yet. I don't think that it's Ellerbeckia. A puzzle for us to solve. I like puzzles. Well, since it seems like we're not going to see very many of the organic-y things that I was hoping we would see, that we never get to see, like a dinoflagellate, because they're always destroyed. Was another little thing that got squished. Squished. Why don't we run over to one of these samples that actually was processed, and let's see how much better they look, or if they look any better. Oh, look at how clean that looks, without all the junk on it. Look at all the diatoms. They're just so pretty. Not the best distribution. They're a little clumpy, but you can see how much cleaner they are. And this is why we tend to process materials like diatoms. Here's something cool. What is that? We're looking straight down on something. It's got these two little pseudoacelli. And then, what are these things? What a cool looking diatom. Oh, what are these? It's got a little forest of star-shaped trees on the front of it. Cool. Also, there's something going on in these holes. Oh man, you know how I feel when I see holes and there's holes inside the holes? That's the best. Right there. Got those holes nice and perfect inside the holes, with then these star-shaped things on the top of them. What is even going on right now with this thing? That is so cool. I need to adjust the brightness because these are too bright, but that is so cool. The valve face is just crazy. It's like it's got broccoli growing out of its face. What is that even? I've never seen that. Huh. Okay, fix it. Yeah. And we can even still see in the holes. Those things are so weird. We're doing it. We're going to take a 10-minute shot of that. I can come back to chat. We'll figure out what it is some other time, but for now it looks really neat. What? Nothing has happened in the chat since I left? That's crazy. Maybe it's just stopped showing me things. No? Chat's just gone silent. Cool. It's totally fine with me. We can all just sit in silence, listen to me talk. If only I could also not talk. That would be even better. Let's see. I'll fix this. I can look around to see if there's anybody we could raid. Oh, Twitch is just acting crazy, that's all. Am I still online? I feel like I'm still online. It still says I'm recording. Maybe the chat's just broken on Twitch. It just says error loading data. I've never seen this happen before. Oh, it's come back. Twitch is just being crazy, I guess. Maybe nobody can talk. Well, whatever's going on with Twitch, this is pretty awesome. A+ on whatever this diatom is. What a crazy view of it. Hopefully you can still see the stream. Guess I can check on my phone. Yeah, all of Twitch seems to be broken. Bitrate's fine on my end. Just nothing's updating. It's just kind of broken. Well, I'm just going to continue to stream and collect crazy images for a little while, and then we'll see what happened with Twitch. Hopefully it's not on your end going crazy as well. My super cool image broke Twitch, apparently. I do have a following list again. And I can see other live streamers. For some reason, chat's just not working for us. Well, it'll be okay. Once we get done collecting this image, I'm going to zoom out, get one more image from a sort of a wider view than this one. And while that one is loading, I think we'll find somebody to raid. So if there's some reason the stream isn't working, it's nothing I did, but it's been kind of nice having everybody here today. Had a pretty full house again, and lots of cool things happened. We had a big raid from Last Miles. We had a bunch of visitors, other streamers that are friends of the channel have come in, and a lot of good questions in chat. So, very nice. And maybe next time I will have figured out how to talk while people are also talking in my ear. And I can just use the headphones for text-to-speech. Possibly, if Sarah's out there and we figure out what we're going to do with the lizard stuff, that might be what we'll do on Wednesday. So for people who are interested, our next stream will be Wednesday, 1 p.m. Eastern Time. And we may be doing live dissection of lizards, or maybe we'll be looking at some more diatoms. We'll see. So this image is almost ready. I'm just going to put down, it's some sort of odontelloid. And what a cool looking diatom that is. So we can zoom out on it, and maybe this will just be our last image right here for the day, since how Twitch is acting goofy anyhow. These cool little pillar-like structures standing up above the surface are really neat. And then these ones with all of those little things around them. And there's 3 on the bottom and 2 on the top. Really neat looking diatom. It's still in focus, and we still have everything the way we like it, so I can just go ahead and hit that image. And we'll look for somebody to raid. And since how nothing's working with the chat still, and I can't tell if people can even see the stream anymore, I want to say thank you really quick to Pacific Plankton and to Del Maximum for hanging out with us today, for all the great questions that we got and all the follows. And we even got a subscription in there. And I think probably what we'll do is maybe we'll go raid Little Chook, because we haven't seen Little Chooks in a while on stream. And so she does really cool drawings, mostly with chickens, and right on screen live drawing artwork from her iPad using Procreate, which is a software that I started using recently as well. So we'll bounce over to there, and I want to thank everybody, despite the weird ending here to the stream with the chat not working for me, and Twitch sort of goofing up. Have some really cool looking diatoms that I took pictures of today. Some of those will be shared on Instagram later, or in the Discord. So I can't tell if my bot will work or not. I'll just type the Discord command in there. It doesn't seem to be like my bot's responding, but maybe it's just because everything on the channel's disappeared for me. And hopefully, if I missed anything, you can catch us on the Discord over there. So let's see. I'm gonna hop into here and start a raid, and we'll raid Little Chook. See if that worked at all. It doesn't seem to be working either. can't really get any of the controls to work. So maybe we'll end up without any raid. Or maybe I can just try refreshing this and see what happens. I'm still streaming, or at least it seems like it. I'm not getting any kind of a response from here. Alright, so I'm just going to go ahead and raid since how we can't get the channel systems working correctly. And it was nice seeing everybody today. So, oh, the quick action won't even work. Nothing is working. Yeah. Alright, who knows what happened? Something's screwed up with Twitch. I tried. See everybody later.